right, so now we're going to talk about electrophilic aromatic substitution reactions that take place with not just benzene all by itself, but these benzene derivatives that we've been talking about, right? So the real question is like, what is that group that's already on that ring? How is that going to influence the reaction? So, right, so let's just start with the simple one. Toluene has that methyl group on there. If we wanted to perform a nitration reaction on toluene compared to benzene, there are a few questions. Like, so for example, we learned about these different positions. We have the ortho positions, the meta position, and the para position. Ortho. Where is that nitro group going to go? Is it going to go to all of them? Is it going to prefer one position over another? What, right? Another question that we can ask is about the rate of the nitration reaction of toluene compared to benzene. So it turns out that toluene will react much faster than benzene. The methyl group is, I don't know if I would call it electron donating in the strictest of senses, but basically it will activate the ring, and we'll see how here in a second. But nonetheless, if you want to compare reaction rates, it does react faster than benzene. And then with regard to the selectivity, the regioselectivity, so where does it go? The ortho meta are para positions. Let's just take a look at the reaction results that we would get. It turns out that the ortho position is the most popular. 63% of your product would be in the ortho position. Only 3% of the product would be in the meta position. And so the last bit, the 34% that remains, would be in the para position. So basically, when you're starting with toluene, you don't get any meta product. You only get the ortho and para products. And you can just sort of note, why do we have, right, if these are my ortho positions, and this is my para position. Notice that I have about a 2-to-1 of ortho compared to para. That's simply because I have 2 para sites and only 1 ortho. So, I'm sorry, I have 2 ortho sites and only 1 para site. Okay, so let's see if we can explain why these positions, the ortho-para positions, are preferred for toluene. So in the first step, if it were going to be in the ortho position, I'll have this attack. Well, this would generate this type of carbocation here, where the positive charge is now, where that methyl group is. We know that just like tertiary carbocations are stabilized, this structure right here is a particularly stable carbocation because of hyperconjugation that you get from that methyl group. It'd be even more stable if instead of a methyl group, it was an ethyl group or anything like that. Okay, so when I'm drawing my different sigma complexes, the different resonance contributors in my sigma complex, this one jumps out in particular as extra stable because of where that positive charge is. If I were to do it in the meta position, I can draw all my different sigma complexes for this. Well, so first, I guess, we have our bond attacking. Now the nitro group is on the meta position. Notice nowhere here do I have that nice stabilized carbocation that's located at the base of the methyl, right? When you're doing your sigma complexes, your positive charge is jumping to every other carbon, and so it just misses that carbon there. Now, if I did the para position, I should have drawn my arrows better so that nitrogen doesn't have too many bonds. My para position, I can again start with my sigma complexes. Notice that in my second jump here, I again have this nice super stable intermediate where that positive charge is located at the base of that methyl group, being stabilized by hyperconjugation. Okay, so In the case of the ortho attack, I have a particularly stable intermediate. In the case of the para attack, I have a particularly stable intermediate. I don't have such a thing in the case of the meta attack. So that's why the ortho para positions are preferred. If we wanted to use a free energy diagram to illustrate this, we could do so, showing that this gap here, right, which corresponds to the activation energy, is much larger for the meta position than it is for the ortho para. Okay, right, that's just the energy of those intermediates, or in this case, in transition states. And because of that position of that methyl group and that carbocation, for the ortho and para, those transition states are particularly stable. Okay. So again, this is using toluene and the nitration. This is actually just a slide that's talking about what I said before about how you have two ortho positions and only one para position, which explains your 2-to-1 distribution of the ortho to para product. Okay, now let's move on to another group. This is anisole. So we have this methoxy group. Turns out that anisole is way more vulnerable. I don't know how to say it. Way more active in electrophilic aromatic substitution reactions than benzene, 400 times more. And it's because the methoxy can donate electrons to this ring through resonance. So what do I mean by that? So this pair of electrons can come down, and then that will put a negative charge on that. So these are basically just all these different resonance contributors I can draw. Again, so now each one of these successive resonance contributors is just going to be bouncing that negative charge around that ring, stabilizing it through resonance before it eventually makes its way back. And I get my starting structure again. So notice why would this electron donating to the ring make it more likely to undergo an electrophilic aromatic substitution? If you just think about it simply, you're pushing electron density into the ring, right? That can be sort of visualized by this negative charge that we have bouncing around. And what role does the ring play in these reactions? It's a nucleophile, right? So by pushing more electron density into the ring, I'm making it an even more potent nucleophile, right? Nucleophiles are electron-rich species. Electrophiles are electron-poor species, right? So by donating electrons to this ring, I'm making it an even better nucleophile by making it even more electron-rich. And then if we want to see in terms of the regioselectivity of the distribution here, we see that we get 31% of our product is para, only 2% ortho, only 2% meta, and 67% para. So again, we can sort of basically say that this is not going to be a meta director, but it is an ortho para directing substituent. Notice that our distribution kind of flipped here. I actually have less ortho than para. That has everything to do with the size of this group here. These ortho positions are just more sterically hindered than the para position. Okay, so that's why in the case of any bigger, bulkier groups, your steric hindrance is going to be a factor. All right, and we can kind of do the same thing showing why that particular, the ortho and para positions are preferred. Again, it has to do with the fact that in these structures, you can have that positive charge in your, when you do your sigma complex, you're going to have that positive charge at the base of that substituent. Same thing in our para position here. They did a very roundabout way of showing that it's being stabilized by the oxygen. You could actually just, if we're going to start out with this structure here, I can show that that oxygen is going to help stabilize that positive charge by donating that pair of electrons down. That brings me to this structure here, right? And it's really just showing how that carbocation is extra stabilized if the attack happens at the ortho position. Same thing down here. Again, they did a really roundabout way. the easiest way to have shown it would have been to just show that starting out with that positive charge at the base of that substituent, this pair of electrons can come down and help stabilize that positive charge, right? So that would lead me to this structure here. Same argument as before. And again, we can illustrate that with our free energy diagrams. Here, the bottom line is that transition state is just much more stable in the ortho and para situations than it is in the meta. Okay. The nitro group, we had sort of mentioned this before in passing, but now we're going to show exactly what that means. The nitro group is a deactivating group, meaning that it is going to withdraw electrons from the ring. Okay, so let's just show how that can be done, right? Notice the partial positive charge on the nitrogen, meaning that it's ready to accept a pair of electrons. Of course, we got to make sure nitrogen doesn't have more than 4 bonds, so that pair of electrons comes up there. And notice that that now means that I have a positive charge bouncing around my ring. Okay, so all these are just going to be different structures that have this resonance stabilized positive charge bouncing around the ring. So why would that make it less potent for electrophilic aromatic substitution reactions? Because again, the ring is playing the role of the nucleophile. Nucleophiles should be electron rich. I have this electron withdrawing species that's taking electrons out of that ring, making it a less potent nucleophile. So the nitro group is an example of an electron withdrawing group, which makes it deactivating relative to these electrophilic aromatic substitution reactions. Okay, so then if I want to look at the distribution of products that I get for this, if I'm going to nitrate a nitrobenzene, my ortho product, I'm going to get 6% of that. 93% of my product is meta, and only 1% is para. So in the case of nitro, we're going to say that it is meta directing. Basically, aren't going to consider the fact that we get any ortho para product. Vast majority of our product is going to be meta. And notice that it is 100,000 times slower of a reaction than if we just started out with benzene by itself. Okay. We can do the same sort of thing to illustrate why that would be. And here it's actually interesting that the culprit is going to be the fact that we again have, in the case of the ortho attack or para attack, these positive charges. In one of our sigma complexes, we have a positive charge that's at the base of the substituent. In this case, these are bad. Okay, and let's just draw out the nitro group to sort of illustrate why that would be. If I have a positive charge here, if I'm going to draw out that full nitro group, remember my nitrogen also has a partial positive charge, or formal charge of +1. So now we have this carbocation, which is positively charged directly next to this nitrogen, which has this formal charge of +1. So that's particularly unstable of a position for that carbocation to go. In the meta structure, notice I never have, because these positive charges will jump to every other carbon, I never have it at the base of that nitro group, so I don't have the same problem. Just to sort of note, different from the activating groups, instead of having a resonance contributor in my sigma complex that's particularly stable, instead I have resonance contributors in my sigma complex that are particularly unstable, right? Doesn't mean that there's anything extra fantastic going on in the meta position. It just means that the ortho and the para positions are extra bad. Okay, so if we wanted to sort of illustrate that, again, using these free energy diagrams, just showing how this now has a huge energy gap for the ortho and para because of the position of that positive charge. We don't have the same problem with the meta. So we would say the nitro group is a meta director. I'm going to use these phrases, either you're an ortho para director or you're a meta director. Most of these, this is actually sort of true for almost everything except for the halogens, but let's just sort of take it at what it is for now. When your substituent is an activator, meaning that it speeds up the rate of those reactions relative to benzene, it's going to be an ortho para director, right? Those are going to be the sites that are preferred. If it is a deactivating group, something that's slower reacting, it's going to be a meta director. So we would call this ortho para director, and this would be meta director. And again, activators are electron donating groups, right? This is all, we're still talking about these electrophilic aromatic substitution reactions. So electron donators are putting more electron density into the ring, making it an even more potent nucleophile. Deactivators are doing the exact opposite. They are electron withdrawing. Okay. Halogens are actually the exception to this rule here because they kind of play both sides. They are deactivating in the sense that they withdraw electrons by induction. So that's like just by virtue of being electronegative. This would be an electronegative bond where chlorine has the vast majority of the electron density. So the halogens are deactivating, but they are still ortho-para directing because they can stabilize those particular positions through resonance, okay? So they're kind of weird in the middle groups because they're deactivating, they withdraw electron density through induction or just by virtue of being electronegative, but they do have these extra electron clouds that they can donate to the ring to stabilize the ortho-para positions, making them ortho-para directing. So let's just summarize real quick. All these different groups that we were talking about, we sort of talked about a few examples from each, but now let's go down and see. We have strong activators. These are things that all have pairs of electrons that they can readily donate into that ring system. And they are ortho-para directing, okay? To be honest, I'm a little bit surprised that the ethers aren't also in that group, but I've seen them there before, but this is what our textbook says. So we're going to consider them to be the more moderate activators. All right. So you have these ethers as well as, you know, your esters or your amides. Notice here that you have a group here that's ready to donate electrons to the ring, but you also have these carbonyl groups here, and they have a little bit of a moderating effect on these substituents because, yes, you again have this resonance structure where you donate electrons to the ring, but you also have a resonance structure available where the electrons go in the exact opposite direction. Okay, so in that case, that's not doing anything. This particular resonance contributor isn't doing anything to increase the nucleophilicity of the ring. So that's why these aren't strong, but rather moderate, but they are still ortho-para directors. Okay. Weak activators. Again, these don't donate electrons through resonance. They instead stabilize the charge in that ring, the positive charge at the ortho-para positions through hyperconjugation. But nonetheless, these alkylated groups here are considered to be weak activators and ortho-para directors, right? So any sort of an alkylated benzene ring will be weakly activated and ortho-para directing. I just note the bigger this group gets, the less likely it is to have substitution. Let's actually use this. The less likely it is to have substitution at the ortho position, the more that para position is going to be preferred just because of sterics. Now flipping it, talking about the deactivators. So strong deactivators, we talked about the Nitro Group as a strong deactivator. We also have what would be like this ammonium type ion where again, the nitrogen has a positive charge. So it's going to be pulling electrons out of the ring. Another one is actually going to be when you have a chlorine on there that's fully halogenated, okay? And in particular, if we have, this one's going to be pretty important. I would say these two right here are going to be the most important because especially when X is bromine, we actually know how to make that using some of the reactions, using one of the reactions that we learned about in chapter 17, okay, specifically talking about when we use NBS. So these two are going to sort of be the most important strong deactivators. And remember, those deactivators are meta-directing. Moderate deactivators are going to be when you have a carbonyl group directly next to the ring. Oops, let's do a highlighter. Notice that in each of these, you have a carbonyl carbon directly bound to the ring. So this can withdraw electrons, right? That's what it meant to be a deactivator through resonance because of this particular resonance structure here. And then we can bounce it around, draw all the different resonance contributors. But again, this illustrates the fact that this is a deactivating group because it's taking electron density out of that ring, making it less potent of a nucleophile. Two other groups that would be considered to be moderate deactivators would be the sulfano group, which we know how to make this one, so that's pretty important, as well as if there was a cyano group on the ring, that would be moderately deactivating. All of our moderate deactivators are also meta-directing. And then the one that kind of falls in the middle, we have, again, these are weak deactivators, but they are ortho-para-directing, and those are all the halogens, so any halogenated benzene. Again, notice that this is the only deactivating group that are ortho-para-directors. With the exception of the halogens, all the deactivating groups are meta-directors, and all the activating groups are ortho-para-directors. So just to sort of summarize things here, I created this slide that just has a nice little summary of everything for everybody. Again, all of our activators are also ortho-para-directors, with the exception of the halogens, which is a deactivator, but ortho-para-directors. All other deactivators are meta-directing. Okay, so just keep that in mind.